So basically, it's not just me, Philip Kriowski, but also my colleague Justin Knappheide. And we work for the embedded systems architecture, for the group of embedded systems architectures for signal processing at University Potsdam and as guest scientists at Fraunhofer Heinrich-Hertz-Institut in Berlin. And we mainly develop a network-attached deep learning accelerator for FPGA clusters, which we develop mainly using SpinalHDL. The outline is as follows. I'm going to give a quick motivation and some CNN basics with focus on training as we do training. And then I'll briefly cover the implementation, and Justin is going to get into some spinal specific code details, which I think we're all interested in. So for the motivation, well, as DNNs grow in size and training data sets grow in size, there's an ever-growing demand on computational resources. FPGAs seem to deliver promising results in terms of energy efficiency. In terms for inference, there's already a lot of data out there, but for training, it lacks data. We will require a simple and fast workflow to iterate over various state-of-the-art designs so that we have some kind of functional way of describing a network, like let's say in PyTorch. Therefore, we want to introduce our easy-to-use framework for DNN training on a cluster, which should be able to run state-of-the-art DNNs and to obtain reliable data in terms of energy efficiency and performance metrics. So a brief introduction on CNN basics. So what we see here is basically an inference of a neural network. Basically, a neural network consists of a number of layers connected in acyclic graph, where you input a bunch of, let's say, images to the left, and then it outputs a number of labels to the right. The different layers comprise of, basically in this, with convolutional neural networks, obviously convolutions, which basically compute weighted sums. But you also have numerous other layers like max pooling, nonlinear activation functions, fully connected layers, and so on and so forth. As we cover training, basically the training part is that basically we run an inference, but and we get a label in the end, but also we provide a, let's say, ground truth label from which we compute an error, which we then backpropagate through the whole net to compute parameter gradients to then, after each batch, perform weight updates to, in the end, learn and gain better accuracies. So what we take away from this slide is that basically the computational complexity from an inference is roughly a third of the computational complexity for a given number of images, as it's with training, because you need to backpropagate the gradients. So you apply chain rule over and over. And for layers which have parameters, you need to compute the parameter gradients also, which after each batch you update. So you could obviously run it non-parallelized, but then it would be very slow, obviously. So basically there's different parallelization techniques, which I'll briefly cover. So you can have data parallelization, which is pretty much used everywhere with GPUs, where basically you split the inputs and compute the whole training on different devices. And basically you split the workload as you compute some parts of the images on each device. Another approach is the layer parallel approach, which we basically mainly exploit. So you put different layers on different devices, and then you kind of have it in as a streamed flow through the number of devices. And just for a little, let's say we use it for more fine granular partitioning. You could also, if let's say there's a very computational complex layer, you could slice the layer and put parts of it on different devices. All of these techniques come with their ups and downs, obviously. So for the data parallel approach, where it works well on GPUs, that's why it's widely used. It introduces a communication overhead for weight updates after each batch for training. And well, a big minus is that the whole net must fit on each device, which is not possible for our FPGAs. The layer parallel approach works well on FPGAs, and we can have layer-specific implementations for the different layers. What is just a little side note, the batch normalization is not applicable on this layer parallel approach, as data streams through the cluster, so therefore you can't really normalize over a whole batch. We use a promising alternative, the online normalization, which basically is a moving average-esque filter. And yeah, with the model parallelization, we basically it enables us for more fine granular partitioning of the network on the cluster. So now I'm getting into the mapping of the network of layers on an FPGA cluster, let's say from top to bottom. So we have an ambiguous network as shown 2 slides before. So it can be sequential layers with some forks and joins, and basically we want to support that we can map an ambiguous number of layers with arbitrary acyclic connections on a set of FPGA clusters in an arbitrary order to support efficient placement. So basically the inputs and outputs are provided via PCI Express, and the FPGAs communicate with each other via 40 gigabit Ethernet at the moment via plain UDP packages. At the moment, our cluster consists of 6 area 10 FPGAs, but I'm not going to get into these details too much, as we're going to focus on the implementation part, on the spinal part later on. Each single FPGA is structured as follows. Basically, each FPGA provides a UDP stack, PCI Express, and some command and control Accelerator interface, and DRAM, where we basically implemented a socket. So from the socket down to the layer, it's all written in Spinal, which handles all the AXI communication stuff, and basically gives us a net where we can implement a number of layers which potentially can communicate to each other on chip via valid ready handshake streams and via UDP to neighboring layers on other FPGAs. We use plain UDP for intra FPGA communication, and basically we get some resource constraints per FPGA for the later on the planning stage of the network. So basically we have a maximum number of block RAM, the number of DSPs which we want to exploit, and bandwidth and DRAM, limited bandwidth and Ethernet and DRAM bandwidth. All right, so for the implementation workflow, it's basically structured in 4 parts as follows. So we enter a model description in a functional way, like let's say in PyTorch, and a cluster description. The cluster description basically comprises of the numbers we've seen in the layer before. Then we feed this into a planner, which emits node and node graph specifications. Basically, the node specifications correspond to the single FPGA as seen in the slide before, and the node graph description corresponds to the connections in between the number of FPGAs within the cluster as seen 2 slides before. While using these, we use SpinalHDL for each FPGA, which then for each FPGA, with the help of the node specification, emits hardware description files in Verilog and some instance details, let's say offsets of DRAM addresses and so on and so forth. As we are currently using Intel FPGAs, we use Quartus as a synthesis and emit bit files for our FPGAs in the cluster, which we then program and use some client in Python, which basically handles the training. So it loads images from and labels from ImageNet, runs the cluster, and offloads train parameters for the training. Basically, we have run MobileNet v2 on this cluster already. It showed promising results, but yeah, we are currently working on that, so that's why I'm not gonna get into this anymore. But yeah, I'm gonna hand over to Justin for some code details.
Yeah, so that was the general structure of our accelerator, but there wasn't much spinal specific in there. So we figured we just show with a couple of snippets of code from our accelerator, yeah, why we chose SpinalHDL and why we like it so much. Yeah, so as a first example, you can see a very simple layer from our networks, the cross entropy loss gradient, which is often just the last layer in a net. So it takes a computed results y and an expected result or expected class C and computes the gradient y prime. And yeah, as you can see, it takes input and expected, so inputs and outputs as stream interfaces. So input is y, expected is c, and output is y prime. And yeah, the stream interface allows us to write this formula out in a kind of very straightforward way. So in 910, you can see we first compute the exponent of y, which we will need twice. So we instantiate a forker that then gives us a .get method, so we can get multiple copies of that stream. So for the denominator, we need to accumulate that with .accumulate. Oh, I forgot to mention all these methods .x, .accumulate, etc. We define to wrapper the corresponding Quartus IP. So yeah, we have a very compact way of instantiating those. Yeah, so we have the denominator computed, but that takes a while. So we need to buffer the numerator for a bit in 913, and then we can just divide them by each other in 914. So that takes care of the first term. The second term, this delta IC, is basically just C one hot encoded, just not in space, but in time. So we take the expected input C, repeat it while counting up, and yeah, get out just a Boolean flag that is 0 normally and 1 if the channel, the value matches the expected channel. Yeah. This one hot encoded stream we can then map to floating points, so yeah, that we can subtract it from our first term, which we already computed, and yeah, we're done. So this is of course still not as compact as the formula on the right, but it is a direct hardware description, so we can still see all the, we still know exactly which registers, what signals will get generated, but don't have to worry about the handshaking between all these different streams. And we can still tune Fmax, for example, by adding stages somewhere or implementing parts of this in a more optimized fashion. So of course you could just use VHDL or Verilog and do the same thing, just define a separate component for each of these functions which we defined on stream. But yeah, then you would have a ton of code because you always need to define your signals separately and instantiate your component and connect them up. Yeah, and that's hard to read and even more painful to change if you need to modify something. Yeah, so that was to demonstrate why we originally chose SpinalHDL just for this nice stream data type. The next two examples are more of suggestions. What we found, what you could do with all this general power, more abstraction power you get with SpinalHDL. Yeah, so the first example is assume you have some signal, for example, just counting up how long a stream stalls, and you want to know that signal during runtime. That's of course easy when you're simulating. You can just open the trace and look and find your signal. But in hardware, it's a bit more annoying. Typically, you would probably just use SignalTap or whichever logic analyzer your synthesis program provides, and manually add that signal in the GUI, and then rebuild your design and look at it that way. But of course, instantiating a whole logic analyzer is pretty expensive. You have memories, keeping track of the history of your signal, and also of the trigger, and you also have triggering logic. So instead, it would be much nicer if you could just like write, as in line 3 in this example, monitor my stall count signal and add some documentation string so you can find it later. And then once you have instantiated your hardware, just have some script list out all the signals you wanted to monitor. And yeah, it turns out in SpinalHDL, that's actually really straightforward to implement, as you can see on the right. So the monitor method just stores the signal and the documentation string away for later. And once you're done with all your hardware description, you can call the generate method, which just takes all these signals, pulls them into the top level or wherever you've called the generate method, and connects them up as one big shift register. Also, of course, you need to know or need to calculate the offsets each signal then ends up having in this shift register. And you can connect that shift register up to whatever interface you have, and you're done. So that's of course specific to your particular design. For us, we just have an Axi4 Lite control interface to which we connect this shift register, and then we can read that out from a Python script via PCIe. This monitor could of course be extended in various ways. So for example, it would be nice to keep track of more information like signal name or the file and line number where your signal was defined. Also the signal type could be nice. So your script printing out all the signals you've monitored can format them properly. Could also use dynamic scoping. So instead of just having this monitor object, maybe have it dynamically scoped values so that for different regions of your design, you could have different monitor implementations that either keep track of more details or just don't monitor at all because that part is already done and you don't want to waste any resources. Also monitor or being able to monitor more stuff would be nice. For example, memories, or really extending that into a kind of small logic analyzer. So yeah, could take a history of the signal and just add some triggering logic, etc. But one very simple application that even works with this very small implementation shown right here is that you can wrapper your assert statements so that during simulation you have a normal assert, but once you're in hardware, you can actually read out a single bit value that tells you whether the assert has triggered or not. So that you still know that in hardware, not only in simulation. So finally, an even more basic idea is that we didn't really like our simulations just terminating right away once an error happened. So instead we use or we defined a trade sim error manager where you can just register your errors, and then you can implement different versions of this manager that handle that in different ways. So on the right, on the left, this no sim error manager would just terminate right away anyways, while on the left, the manager just collects a bunch of errors, and only once the threshold is reached, then ends the simulation. And using dynamic scoping with this inheritable thread local class, we can just select different managers for different parts of the simulation or for different simulations running in parallel. One thing that's not shown here, but that we also did, is we wrapped the assert statement again, so that now during simulation, it also doesn't generate this Verilog assert, but just once again adds an error to the error manager. So yeah, we can keep going with the simulation even though the assert triggered. Yeah. So that was it. Thanks for listening.
Thank you.
Thank you.
Okay, so I think, yeah, there is a few questions. Garas is asking if there is any advantage using FPGA cluster training neural network over using the GPU.
And yeah, obviously we hope that we can prove it. For inference, there's a lot of data out there already, which suggests that there is. To be honest, we couldn't perform decent measurements yet, but especially with cutting all the overhead as having the FPGAs in a network attached fashions, we are quite confident.
So the basic idea is that we can save DRAM accesses because we can more intelligently pipeline our layers together, keep weights always in block RAM. Yeah. At least.
So there is also quite a few other questions, like Shiksu is asking many questions. I will do one by one.
Okay, maybe we can stop sharing and read them ourselves. I don't know, it doesn't work.
I think it's best if I will read it, because then it's registered in the video, in the recording. But yes, it is in the chat. So first question is, what are your novel contribution compared to other CNN accelerators?
First, there's not many out there who do training, so most of them focus on inference, and basically us being able to fine granular partition them on heterogeneous clusters. That's a novelty.
Second question is there an open source GitHub repository about your CNN accelerator?
No, we're sorry, not yet, as it's very much work in progress.
Is it planned?
Well, we have to figure it out in the end. But we can't make sound statements yet.
Yeah, sure.
Sorry.
From BRAM, DSP, PCI Express, are you using black box, or are you at least coding by yourself using SpinalHDL and ITFAIR from Vivado or Quartus?
So for PCI Express, we are using some proprietary IP core. For UDP, a colleague in-house developed the core, and the other one I forgot. DRAM, I guess.
BRAM, yeah, memory blocks.
Block RAM. Yeah, we use the SpinalHDL memory elements, which period.
Okay. And the DSP?
Yeah, as we mentioned, it's the native Intel DSPs, as we are using Altera boards, Intel boards.
So you're using the black box for the DSP?
We're using the black box, which we wrap it into functions for float, and then wrap it as stream methods.
To hide them away. To hide them away.
Yeah, the boilerplate code.
And how to deal with floating point with SpinalHDL for your CNN accelerator? How do you deal with floating point?
We are just using the floating type, which is in the library. We extended it a bit, so yeah, I think some common functions weren't there, but I honestly can't remember which it were.
Yeah. And how do you think about quantization for your accelerator using SpinalHDL?
To be honest, for training, it's quite common to have a floating point of some sort, to be honest, because the boards which we use at the moment support single precision. We just use that and we don't plan on cropping the mantissa or exponent. But well, if different boards arise, it could be. But normally you train on full precision or on single precision and then crop for inference. So that's what we are doing.
Okay. I don't know that domain that well, but isn't quantization more for fixed point processing, or is it related?
Yes, there's two types of definitely for fixed point computation, but also you could, let's say, just use half of the exponent or save some part of the mantissa, and then if the board provides it, you can have let's say use one DSP for two operations. There are a lot of commercial names. From NVIDIA does it, but I forgot the name, to be honest. I think it's NVIDIA Precision or something.
Yeah. Is it's a question from Com 744, which is asking if there is error management. Is the error management you implemented public for the simulation, I think?
Also not, but I think I think it's a minimal working example, which we have in the slides.
Yeah.
But yeah, we can think about it.
Yeah. I mean, yeah, generally, if you think some piece of code are really generic, do not hesitate to do a pull request or to discuss about it.
Yeah.
Okay. Yeah, I think that's it for the question.
Okay, thanks.
Thank you.
I stopped the sharing somehow.
I think so, yeah.
But how?
I think the sharing is stopped already. Is that possible?
Ah, could be. Yeah. Ah, yes. Nice. All right. Thanks.
Thanks.